Okay, so we're going to get started here with some trig. And before we get started, this is going to be like our prerequisite sections. So we got Algebra 3 trig prereqs, and this is prerequisite section 2. We're just going to skip over 1 because 1's pretty self-explanatory. And this is going to be real numbers. So for those of you that are looking at this from Algebra 2 or even Algebra 1, this is going to move quick. It's supposed to move quick for trig because it's supposed to be a refresher. So, whole numbers. Basically here to summarize, a whole number starts at 0 and it goes up. All positive numbers and 0 are whole numbers. Okay, so we're talking no fractions yet. We're talking no decimals. We're talking no integers. We're talking no negative numbers. So keep that in mind. Integers. Okay, integers are negative numbers and positive numbers and 0 in the middle as well. So keep that in mind. But once again, there's still no fractions and there's still no decimals. Okay, this is negative and positive numbers the whole way out to infinity. That's what this dot 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 means, and it also includes 0. Rational numbers. Rational numbers are whole numbers. Rational numbers are integers. Rational numbers are fractions and decimals. So the whole point I'm getting at is a rational number is 0, 1, 2, 3, 4, a million. It's also -1, -2, -3, -million. And it also includes 0. But most importantly is the fractions that terminate. So we're talking like 3 over 2. We're talking 4 over 3. Okay, rational numbers are fractions. They could be, 3 over 4, for example. Those are fractions. Decimals like 0.6, 0.8. Okay, those are also rational numbers. So here are some examples for you. Like this one, you have a fraction a over b, you have 1 over 2, 4 over 3. Even this, even though it simplifies to 4, it's still going to be a rational number because it's a fraction.
The dread pirate Steve be in no man's debt.
Alright, so irrational numbers, they are numbers that never end. Okay, so for example, the biggest one that you guys might know as an irrational number is pi, 3.1415926535, and I don't remember the rest off the top of my head, but that is an example of an irrational number because it doesn't end. Another example might be something like root 2. Non-terminating numbers, that basically means that they'll never end. Terminate means end, so numbers that never end is kind of the same way I said it. Those are the two big examples to keep in mind when we're talking about irrational numbers, pi and root 2. They are never going to end. The decimal keeps going forever and ever. Okay.
Is that your routine or performance of Cirque du Soleil?
Prime numbers. It's a number that's divisible by 1 in itself, and that's it. So some examples of some prime numbers might be like the number 7. 7 you can't divide by 2, you can't divide it by 3, okay, you can't even divide it by 5. The only number that you can divide 7 by is 1, right? 7 divided by 1 is 7. You can also divide the number 7 by itself. 7 divided by 7 is 1. So it's a number that you can divide only by 1 in itself. Those are examples of prime numbers. So 2, 3, 5, 7, those are all examples. 11 is another one. 13 is another one. All right, it's not all odd numbers because if you look, right there's a 2. Okay, so it's mostly odd numbers that would probably be prime, but notice how it's not all odd numbers that are prime. So when we are taking a look here, we are doing complex numbers. All numbers, including imaginary numbers, are complex. Okay, so before we were talking about every single number. We're talking about real numbers. We're talking about rational numbers. We're talking about integers, whole numbers. Now we're talking about numbers that don't exist. And if you remember from Algebra 2, imaginary numbers were the numbers that had i's in them. And that is what we're talking about here with complex numbers. Imaginary numbers are numbers with i's, like I said. So, like I plus 3, 4i, negative 8i minus 4. These are examples of numbers with i's in them. This is just a little chart here so you can see what everything is made up of. And if we start here at the bottom and work through, notice how an integer is made up of a whole number, it's made up of negative numbers, it's made up of positive numbers, and 0. So notice how all of those go into integers. Okay, rational numbers are made up of integers and every single one of these as well because they're all rational as well. Over here, irrational numbers, notice how it doesn't connect to anything because all of these, they aren't decimals that never end and they aren't fractions. But real numbers are everything that's real. That's why this is made up of all of those elements because real numbers contain every single possible number that exists. And then there's complex numbers. Complex numbers contain real numbers, but they also have i's, which we just talked about. So that's like a little chain there to see how all the numbers connect, which would be great to understand for a test if we were to give you true and false questions that consisted of like, are all complex numbers, 0? Are all complex numbers negative? Are all negative numbers complex numbers? Well, you could follow this little chart and work backwards to find your answer. Alright, so there's me with Betty White. And Betty White and myself are just going to help you figure out properties of addition and multiplication, which you should already know. So the commutative property. You should know this by now. Basically what it's saying is if you add two things together, you can basically swap the order if you wanted to, and you'll still get the same answer. So for example, if I had 2 plus 3, I'd get 3 plus 2. That's all it's saying, something you should already know. Multiplication is the same. If you multiply two things, if you reverse the order, it's not going to matter. That's basically what this is saying. 4 times x and x times 4 will both give you 4x. It doesn't matter the order there. Okay? Okay. So associative property. Okay, associative property of addition. Basically, this is just talking about grouping. If I group these two together and then add it, or if I group the first two together and add it, it's not going to make a difference because addition doesn't make a difference here with the order. So the point is, if I added these two first and then added the 2, or I added these two first and then added the 4, it's still going to give me the same answer. See, that's 7, that's 2, that's 5, that's 4. Both are going to give me 9. Multiplication is the same way. The order here is not going to matter. So the point of getting it is whether I did those two first and then the one out in front, or I did those two and then the one in the back. It's not going to make a difference. So here's an example. If I multiply these two and then by 8, or if I multiply these two and then by 3, it's not going to make a difference. Down here, 2 times 3 is 6, 8 times 2 is 16. Both, when I multiply them, will give me 48. So, just something to keep in mind.
Hey, Doc, we better back up. We don't have enough road to get up to 88. Roads? Where we're going, we don't need roads.
So, identities, the additive identity. Pretty self-explanatory here. When you take a 0 and you add it to anything, you'll get what it was before. So the point I'm getting at here is 6 plus 0, it's going to be 6. Multiplicative identities is when you take 1 and you multiply it by anything, you're going to get what you started with. So 8 times 1 is 8. All right, 9 times 1, 9. 10 times 1, 10, right? Whenever you multiply something by 1, you get what you started with. Whenever you add 0 to something, you get what you started with. So just something to keep in mind.
Oh, thought you were going to tell me.
Inverse. Now, additive identity for inverse. When you take the same thing, negative and positive, and you add them together, you should get 0. So a negative 5 and a positive 5 will add together to be 0. A negative 6 and a positive 6 will add together to be 0. The multiplicative inverse, though, is the reciprocal. That's what this is right here. If I have a, the reciprocal of a would be 1 over that. If I multiply those two together, notice how these a's will just cross right out, because I have 1 on the top and the bottom, leaving me with just a 1. So 6 times 1 over 6 will give me 1, because whenever you multiply it by the reciprocal, you'll end up getting 1. Alright, and when we come back here, we will finish up with our properties, talking about the distributive property and do some examples.